Okay, we're going to finish off our review by talking about some more muscular system review. All right, and so here are our objectives for this lecture. So excitation, contraction, coupling. We essentially finished with this on the last video. All right, and so got a different picture. I think I actually like the one from the last lecture a little bit better. So the way that it works, action potential comes down the neuron, acetylcholine's released. That acetylcholine activates ligand-gated sodium channels. Sodium comes in. This allows for depolarization, or this allows for the activation of voltage-gated sodium channels, which cause depolarization. That action potential goes all along the sarcolemma and the T-tubule. We activate those DHP receptors, which are voltage-gated calcium channels. And this causes two things. One, calcium goes into the cell from the T-tubule, and the ryanodine channel, which is a mechanically gated calcium channel, opens. The opening of that ryanodine channel allows calcium to leave the sarcoplasmic reticulum. Calcium binds to troponin, which moves tropomyosin out of the way. Myosin binds to actin, and we have what's called a cross bridge. This is excitation-contraction coupling. Okay, so to give you an idea of how calcium and troponin and tropomyosin and all that work together, I'm going to give you my analogy about my daughter dating. Okay, so actin is my daughter. Myosin is the dumb boy that she wants to go out with. I am tropomyosin. My wife is troponin. Okay, so I don't want my daughter to go out with a dumb boy because I'm a jerk like that. I've never done this, by the way. And so what ends up happening, let's just say the kid's he's a good kid, talks to my wife, and ultimately what happens is my wife convinces me it's okay. And so my wife, acting like troponin, moves me, tropomyosin, out of the way, and then actin and myosin get together and form a cross bridge, and then they come home at 7 o'clock and they're in the evening and they're done with their date. All right, so kind of one way to look at it. Once we have this cross bridge, well, that just means we're producing force, but it doesn't mean we have a muscle contraction. And the way that works is with the sliding filament theory. The sliding filament theory, there's several steps, but each step kind of has two parts. Something happens with ATP, something happens with actin and myosin. So when ATP binds to myosin, actin and myosin separate. Okay, and we're going to start up here at the top. All right, and so now we're here in between, I guess we're in between step 2 and 3. So right here, ATP binds, actin and myosin separate. All right, then ATP is broken down. Now we have ADP, phosphate, and energy. Okay, that energy causes the cocking of the myosin head, and so we see that here. When that happens, actin and myosin also reattach. The phosphate leaves here, and then we have the power stroke. And so now we're pulling actin towards the center. ADP leaves, and now actin and myosin are tightly bound and remain that way until ATP binds again. Then they separate, and we go through this whole thing. That's the sliding filament theory. It's something that's been around for 50 or 60 years. Actually, I think a little bit longer. I think it was 40s when this was when this theory was developed. Well, now we have something called the winding filament theory. Okay, like it says here, sliding filament theory would suggest the filaments slide. However, there's some evidence to suggest that the filaments actually twist due to titin. All right, so titin's activated by calcium, and what happens is it winds around actin. Okay, as a result, we produce more force. It also prevents our muscle fibers from overstretching and being damaged. Okay, and so like we talked about, titin is a stabilizer, but it also helps to increase force production. All right, just think about a spring. Okay, you pull that spring out, what happens when you let go? It releases, right, and it goes back to its original form. Okay, but the titin, like it says here, is also to prevent sarcomere damage. So this leads into motor units. Well, what is a motor unit? Motor unit is one motor neuron and every muscle fiber that it innervates. So on this picture here, we have two motor units. One's purple, one is red. Individual muscles have many, many motor units, and each motor unit has a different type. And so type 1, type 2A, type 2X that we'll talk about later. Now with motor units, the way that they fire is related to the all or none principle. If we reach threshold, if that motor unit's excited, it's going to cause the muscle fibers to contract and contract maximally. Okay, if threshold doesn't happen, then nothing happens. So either you have maximum contraction or you don't. And this leads into the size principle. These things are all related, right? So we recruit motor units in order of their size. We go from smallest to largest. Well, why is that? Well, I like to cook. I like to bake. I make some pretty good cookies. There's some of you in class that have had my cookies and can vouch for that. So what happens is, when I'm making cookies, there's eggs in cookies, right? And so imagine if I picked up an egg using my biggest, strongest motor units. What's going to happen? I'm going to crush the egg. I'm going to have eggshell everywhere, right? So that's not great. And so I use small units first. They produce small amounts of force. If I need to pick up or if I need to use a little bit more force, well, then I'll activate some more motor units. Okay, this allows us to be efficient. It's a build up to the force that we need to do something. Okay. It's also important to remember how the length of the muscle determines the tension or the force that it's produced. Okay, so here notice that at about the typical resting length, we produce the most force. As we go away from that length, either we increase it or we decrease it, then what happens is force production goes down. And the reason is, when we're completely stretched out over here, notice that there are very few cross bridges. Cross bridges are extremely important to force production. More cross bridges equals more force. Okay, here we've got a lot of cross bridges, but the problem is there's a lot of overlap too. And actually there's so much overlap that some of these myosin heads aren't actually attached to actin, plus the muscle's as short as it will go. All right, and so just imagine you've completely flexed your elbow. Well, how much force production are you going to produce with your elbow completely flexed? And the answer is not so much. The last review thing is the force-velocity relationship. As you can see from this figure, as force production goes up, velocity goes down. We produce the greatest force at the lowest velocity. Just think about somebody doing like a max bench press or a max squat or whatever it is. How fast are they moving? Not very fast at all. Some of you are in PE 392, where you're learning how to train clients, and I'm one of the clients this semester. And the guy that I'm working with, he told me to do bench press, and we're doing a lot of reps, very little weight, and I get the bar, and I start really going really fast. I was like, wait, this can't be the normal bar, and apparently he'd given me like the little kid bar. And so I was able to move that thing really fast, but that was because I wasn't generating a lot of force. And so that's how we're going to end our review.